Thank you.
Maybe it is in my presentation. I don't remember this.
Thank you again, Marianne.
Okay, thank you.
So our next presenter is Dr. Stephen Foster, who is a professor emeritus at the University of New South Wales in Australia. Dr. Foster is going to talk about challenges and insights in finite element modeling of steel fiber reinforced concrete.
All right. Okay, good, brilliant. Well, thank you very much. And look, it's great to be invited to give a talk here on Frank's fourth year of retirement. I think it's the fourth year. Thereabouts, COVID intervened in between. And I guess I've known Frank since about 1996 in various ways, developed a great friendship and career. He hasn't changed at all right? So, Frank, it's, it's brilliant. And of course, neither have I. We're all exactly the same as we were, and we had some fantastic times. So when I first was asked, I thought, geez, there's some fantastic stuff I want to talk about, great research I want to do. And time went on. I thought, I'm not going to get to that. So I started to think about what we might do, particularly around steel fibres and some of the challenges of modelling, and that's what I want to talk about today. Particularly, I'm going to go back into the past and look a bit of history, some of the earlier work, and one recent paper. Talk about a little bit about the variable engagement model, a couple of examples, and it's including remarks. I think many of you will know that we invested a lot of time and energy with students in a model which we call the variable engagement model, but I think one of the things that is always nice to know is, well, where did it come from? And it came from this observation. It was a test by Banthi and Trotter, and we're sitting down one day looking at this particular test. It's a single fibre. We always thought if you could take a single fibre and just add them all up, you should be able to get the end result, right? It's a nice way of thinking of things. And we looked at this and said, well, depending on the angle of the fiber's engaged at different points in time, right? You get a lot of initial pull, you get snubbing effects and the like. So this is a fibre at angle of 0, engages quickly. But when you get to fibres up to 45 and 60 degrees, it takes some opening displacement before those fibres actually work for you. So in our domain, where we're looking between maybe 0 and 1.5 millimetres, maybe 2 millimetres, there are a lot of fibres that come in at slight angles that are never going to do anything for you. And this is it. So you add all that, you integrate every fibre on the surface, you add in the concrete component, and you end up with a curve that looks something like that. And there have been various versions of this over time. So that was 2003. That was my first, one of my early PhD students, not my first, Jackie Yenyu Vu, who's moved on to do great work in bridges and ultra-high performance concrete. And this is what it came out to be, really nice. That global orientation factor just comes into the mathematics that comes out to all those working out what the volume of fibres is, simply the aspect ratio of the fibres, the volume of fibres, and the bond shear stress of a single fibre pulling out, which you should be able to get from tests. Right? So if I do a uniaxial test, I can do a single fibre test at the same time and get that. In 2007, a student of mine called Greg Lee developed what that was called VEM. We renamed that later to VEM 1, Mode 1. He looked at shear. And in shear, the end hook has a lot more importance. In fact, when you look at shear, the straight fibres do nothing. They engage really late. So therefore, they effectively don't do anything. So if you don't have a hook, then the fibre doesn't do anything. Now, this comes to a question which I've never really seen answered yet. So what happens when you have longitudinal shear between the interface of a web and a flange of a beam? Do the fibres actually contribute to that? And I think there's some evidence that they do not. That's an open question. The students came after that and said, okay, well, we will put these together and we'll call the unified variable engagement model. So now we have a model that does mode 1, mode 2 and everything in between. And that's a lovely model, really nice. It's fairly simple. We have nice equations for the bond, but it's not my favourite. It's more complex than it needs, and coming back to this simple model that we developed right up front is still the one that I prefer. Largely, I think, because when we look at the interaction between slip, sliding and opening tends to dominate, right? So we do get some sliding, but the amount of sliding is not so much. So I put this down to this is why it's been fairly robust over time. And here's the validation of those, and these are tests where they've done the single fibre test to get the actual bond slip of the fibre. So they've actually got that data input in those. And you can see here the models predict the failure, predict the uniaxial strength pretty well. Okay. All right. So this comes down to then my first example. This is a paper that we presented in Maui. Frank, you might remember, we had a fabulous, I don't remember if you had a car or how we got to the conference venue or walked. You went to the car, it was fabulous. We had these really big, luxurious places. Anyway, it was a fabulous conference. I think one of the things I did mean to mention up earlier, I might mention it now, because I've been hearing the last couple of days about Frank and Pink Floyd, right? That's the pacifist Frank, right? The activist Frank listens to Midnight Oil. That's right, which we found out on one of our great trips. Anyway, so we're in Maui, and so this is not new work, it's 2003 work. But it comes up from the numerical modelling of these tests of Jackie Vu, ultra-high performance concrete beam, 650 deep, span of 4 metres, and so the 2.5% of fibres, 2 different types of fibres, end hooked and straight, 170 megapascal concrete, and this is it. So the model allows you to add all the components, the end hook components, the straight components to get the model here. Now, one of the things, again, just reflecting the importance of this, and I haven't seen much of this in our works, using non-local models. And here in shear particularly, in fibres particularly, I think these models have a really good place to be. If we look at this, we're looking now not at just the influence at the sampling point where we're at, but in its neighbouring region. In this particular example, we have a characteristic length for the model of 50 millimetres. So we have about 50 sampling points of which we are sampling, and we're weighting of those things. So it's not just of that point. That has the advantage of taking out mesh sensitivity, the mesh geometry sensitivities, right? We tend to use square or rectangular meshes. This takes that out to a large extent. So we're looking at 3 different meshes, a 50 millimetre mesh, 20 millimetre mesh and a 10 millimetre mesh, very, very fine mesh. And in 2003, that was computationally intense, but it's not in 2025. Computers obviously increased dramatically in their speed, and therefore it's no longer computationally challenging. All these cases have a 50 millimetre local zone. There we are. So these are the 3 examples. You can see there is no sensitivity in those examples. One of the things I always, again, interesting in this part of the test, it's not much interest numerically or things, but from a behavioural thing, it's actually quite interesting, because this is the end of the test. And I ask people how much load that's carrying. If I took this off, that's still carrying 240 kilonewtons, so it's carrying about a third of its failure load. And you say, how? How on earth is that? The fibres are clearly not doing anything at that stage, right? Of course, it's the pre-stress, given the arching effects on that. So this part of the curve, there are other things occurring. This is the parts of interest, and we see that we don't have any sensitivity there. And this is the failure. This is the 50 millimetre mesh. You can see here, this is the failure crack on the experiment. This one here is the 20 millimetre mesh, and hopefully this one, if it works, there you go. This shows the 10 millimetre mesh and the change in the localisations. All right, and you can see here we're not, with the angle of the crack, it's not dependent on the mesh shape or size because it's sampling the regions around it. There we are. So that's one step before and that's one step after. So again, you can see here the start of the formations of the localisations and the end of it. Okay. So as I said, that was some old work. It was 2003 Mao, 2006 when the publication came out. Let's look at something a little bit more recent. This was some tests we were looking at. We wanted to model these beams. These are a two-span beam, two-span slab. We were particularly interested in the amount of moment redistribution that we could get. So we designed these for plus or minus 30% of moment redistribution. So from the negative, so when you see the notation, when we talk about plus 30%, it means we're taking 30% away from the negative and moving it to the positive, and minus, we're moving it from the positive to the negative. This is 400 by 250, this is 220 by 800, 0.2% to 0.4% steel, 0.7% to 1.4% steel in those two cases. All right, so I won't go through the models, but you've all seen these before. They all have their basis back in the modified compression field theory, at least in this part of the curve, and in this part of the curve it's based on the biaxial strength envelope, fairly commonly used. Same in the tension side. On the tension side, we basically use sort of these fairly simple types of models, and in the fibres as before. On the steel, we can model the steel very different models, the compression and the fibres. Now, first thing I want to point out here, this is not a predictive test, right? We were looking at parametric studies. We wanted to see what happens when we change certain parameters, but we wanted to get the result as close as we could to the experiment. Right? So the model is tuned to the experiment. But I want to reflect on some of these points. All right, so when I say that here, we look at the experimental crack spacings. This region here, the crack spacings in the negative moment regions is different to the crack spacings of the positive moment regions, and we knew those crack spacings, so we put them in. Right? We said, this is what we're going to base the fracture energy on these known parameters. And we'll reflect on this in a moment. In this case here, the characteristic length is 30 millimetres, and you can see here, not unexpectedly, we get very good calculations. This case here, just comparing moment versus deflection. So minus 30% for the beams, plus 30% across. The slabs 0, 10%, 20% and 30%. And you can see the correlation there is pretty good, as you would expect it to be. All right, when we look at the crack themselves, this is the beam experiments and slab down the bottom. The darker lines there are the experiments, the coloured obviously the numerical models over the experiments, and we see again the models are reflecting what we see in the experiments. And so that's the point of this, was then to look at other combinations. We're confident we're starting off at a good point. The crack widths here, we're getting 13% on average there, 8.89, low coefficients of variation. For cracks, that's pretty good. For the strengths, we're in 1% of the 1 to 4% of the actual strengths themselves. Let's think about this then from, okay, what if we don't know this information? We don't have the experimental data. What's important here? If we're looking at strain softening behaviour in fibres, the most important thing is going to be the crack widths. If you don't get the crack widths right, you can't get the percent of the fibre right. What's important? Crack widths, crack spacing. If you can't get the crack spacings right, you can't get the crack widths right. So crack spacings is really important. And this is an area where more research is needed. We've been looking at crack spacing equations for shear on simple models for a different purpose, and wow, they are not only complex to understand, they are messy, they're noisy, the degree of accuracy is well, disputable. So does that matter? Well, that matters. It doesn't matter as much if you've got something like this, where you've got a fairly good plateau. So I might say these other tests, we've been using 5D fibres, and the early tests were 3D or straight. these particular fibres, they've got a fairly low plateau. And if we're looking at maybe 1 to 2 millimetre crack widths at ultimate, it's not going to affect it that much. But this fibre here, this is a twisted fibre, and you see it has a very high softening, right? It's going to affect it a lot. Right? So I think the performance of the fibres is very important here. And if you can get a fibre that performs more uniformly, more likely your model will be not so sensitive to these things. And then just reflecting here on this statement of Darwin and Pecknell, the present model is intended primarily as a research tool. It's too costly to be used in analysis of large-scale structures, and that was in 1976. That is no longer the case today. I saw Jan Cervenka here in the audience with their model Latina, Frank's with model Vecchio 2. These now are tools that can be used in design. And this is it. 1 minute. Perfect. Thank you. All right, so accurately modelling behaviour can be challenging. Crack widths need to be accurately determined. This, to me, is the area we need to put some effort into the research. I firmly believe in the non-local models when dealing with this, because it's really quite sensitive to the actual shape of that failure surface and percentages. And just these last pictures here, yes, we do have kangaroos on the south coast of New South Wales, where we spent a fabulous winter, I think, one day, walking down the beaches, and that's the backyard of our place in Sydney, and I couldn't not send that. So thank you very much. And Frank, can I just say good luck for the rest of your career and time.
So we have time for 1 or 2 quick questions.
That's easy. Oh.
As always, I have questions.
I was expecting Evan, it's okay.
I was wondering about this choice of the non-local model. At a certain point, you said you want to make it 3 times larger than the normal concrete. But if I look at the material test, what happens is you have a very quick, this one.
Sorry, which one? This one here, yeah.
You have a very quick softening and then a long plateau. And my feeling is this very quick softening is more or less the conventional concrete type of softening.
Not really. Conventional concrete, this would be down at about 0.3 of a millimetre, right?
Yeah.
So we're up at 2 millimetres, so we're a factor of 10 times that.
Yeah, I'm not referring to that part. I'm referring to the 0.1 millimetres, a very sharp drop, because...
Oh, this one here, well,
yeah.
Okay, yeah, that's just cracking, all right? So you can ignore that. That's the point of concrete cracking.
Exactly.
You've got that in everything, right?
Exactly.
That's uniaxial tensile strength. It cracks. It doesn't crack to 0. That's the difference there.
But if you think about the localization, usually if you have this sharp drop,
yeah.
There's a point where you already localize everything. But then the question is, why you should choose this?
Good question. Yeah. Look, one of the things you've got to remember, and I think we sort of forget that when we do our tests on single elements, right? One event happens, you get this. Our beams, our structures are not made like that. There is a degree of uncertainty about the cracking layers, right? Nothing ever cracks exactly at the same time all the time. So you get this disputed point of cracking. So you don't get these tendencies for really sharp drops when we start to look at real structures or even real panels. For the non-local model, this becomes even more important, right? Because if you don't take that, you get a very strong mesh sensitivity at that point. So you must take into some non-local effects, even if you just take into characteristic strength of your element size. So if you're using a local model. So.
And you have done calibration of different...
Yeah. The answer is yes, we have done calibration. Thank you very much. Thank you.
So our next presenter is Dr. Fausto Minelli, who is a professor in structural engineering at the University of Brescia in Italy. Dr. Minelli's presentation is about design of steel fiber reinforced concrete elements under torsion.
Okay.